In the last class we saw the dual of the assignment problem. The primal minimizes sigma Cij Xij subject to the condition that one job goes to exactly one person and one person gets exactly one job. So, in a n by n assignment problem, which means there are n jobs and n people, we have n constraints here and we have another n constraints here. So, there are 2 n constraints in the primal. Now, since there are 2 n constraints in the primal, the dual will have 2 n variables. So, we will introduce ui variables corresponding to this set of constraints and vj corresponding to this set of constraints, and therefore, the dual solution or dual will become maximize sigma ui plus sigma vj, because the right hand side in the primal is 1. So, 1 into ui plus 1 into vj, sigma ui plus sigma vj, ui plus vj less than or equal to Cij. Dual will have as many constraints as the primal variables. There are n square variables in the primal, there will be n square constraints in the dual. A typical Xij will appear in the ith constraint here and the jth constraint there. So, it will have the form ui plus vj less than or equal to Cij. So, we also said that we will see how the Hungarian algorithm works with respect to the dual of the assignment problem. So, let us now go to the examples that we have seen and explain how the optimality of the Hungarian algorithm happens, or why the algorithm that we have seen gives us the optimum solution. So, let us look at this example, which is a 4 by 4 example. So, the 4 jobs and 4 persons are here. So, these represent the 4 jobs and this represents the 4 people. So, the first step what we did was we subtracted the minimum from every row. We identified the row minimum and subtracted the row minimum from every element of the row. The first row, the minimum happened to be here, which is 4, and then we subtracted this to get 4, 2, 0 and 5. Now, this is the same as writing u1 equal to 4, u1 happens to be the row minimum. So, writing u1 equal to 4 and subtracting u1 from every element of the first row. Similarly, it is the same as writing u2 equal to 5, 5 happens to be the minimum. So, u2 equal to 5 and subtracting 5, u3 equal to 9 and subtracting 9, and u4 equal to 6 and subtracting 6 from every element. Now, we reduced it to this matrix, the matrix that is shown here, we reduced it to this matrix, and then we looked at the columns one by one and we subtracted the column minimum. The first row, the minimum happened to be 0, that is the same as writing v1 is equal to 0 and retaining the same column. For the second column also the minimum happens to be 0, which is either here or here, which is the same as saying v2 equal to 0. For the third column, the 0 happens to be the minimum, so v3 is 0, and the fourth column the minimum is 3. So, we write v4 is equal to 3 and then we subtract the column minimum from that to get the new matrix, and we also said that this matrix will have at least 1 0 in every row and in every column. Now, this new matrix that we have got, if we take a typical element which is say here, now this 1 has come out of a subtracting 5 at this level and subtracting 3 at this level. So, this 1 is nothing but 9 minus 5 minus 3. So, this value is actually, this value that we have here is C dash I j, if I may call it, C dash I j is equal to the original C I j minus U I plus so it's C I j minus U I plus V j is what we have here. And if the original matrix has all cost coefficients greater than or equal to 0, this C dash I j, which is C I j minus U I plus V j, will be greater than or equal to 0. So, this will be greater than or equal to 0. So, C dash I j will be greater than or equal to 0. Now, when C dash I j is greater than or equal to 0, it implies that U I plus V j is less than or equal to C I j, because C dash I j is greater than or equal to 0 means C I j minus U I plus V j greater than or equal to 0, U I plus V j is less than or equal to C I j. So, the u's and the v's that we have defined through subtracting the row minimum and the column minimum gives us a dual feasible solution. So, this set of u's and v's are feasible to the dual. Now, we look at this matrix and then we make assignments. Now, if we made assignments based on, for example, the first row has only 1 0, so we could make an assignment here. The second row had only 1 0, so we could make an assignment here, and then this goes. The third row has, the first column has 1 0, so this goes. So, we are able to make 3 assignments. Now, if we were able to make 4 assignments in this, then we said we would have got the optimum solution. Now, the motivation is as follows. We are going to make assignments only in 0 positions. So, when we make assignments only in 0 positions, corresponding to these positions, C I j minus U I plus V j is equal to 0, which means the dual constraint there is satisfied as an equation, which also means that the dual slack is 0. So, if this is to be written as an equation, then we need to add a slack which could be some Hij, and that slack will be 0. So, what we are doing is we are trying to make allocations only in 0 positions, which means only in positions where the dual slack is 0, which means we are indirectly applying complementary slackness. So, we would make an assignment Xij will be basic only when the dual slack is 0, therefore, x which corresponds to the primal variable into v which corresponds to the dual slack will be equal to 0 because the dual slack is 0. So, if we are able to make an allocation if we are able to get 4 feasible allocations in this matrix, then we would say that we have got the optimum solution. For this particular example, at this stage we are not able to get the 4 allocations, we have to do something more, but if we have a matrix where an n by n matrix where after subtracting the row minimum and the column minimum we get a reduced matrix, and that reduced matrix means there are some ui's and vj's that we have defined. The ui's are the row minimum, the vj's are the column minimum, and ui plus vj will be less than or equal to Cij, because by subtracting the row minimum and column minimum we make sure that the resultant matrix is greater than or equal to 0, which is here. Therefore, it is dual feasible, ui plus vj less than or equal to Cij, and ui vj's are unrestricted. So, we do not worry about the sign of this u's and the v's. So, doing the row column subtraction and getting a new matrix is equivalent of defining a set of u and v such that the corresponding dual solution is feasible. By making assignments only in 0 positions, complementary slackness is satisfied, and if we are able to get a feasible solution, then such a feasible solution is optimum. Of course, in this example we are not able to get a feasible solution with 4 allocations. So, we do something more. So, we see what we do there and how we explain this. So, we went ahead and we had this solution. So, we have made assignments in, let us say, these 3 positions. We have made assignments, here, we made assignments here, and then we made assignments here. Now, these 2 zeros are not assigned and they are crossed. Now, at this point we said that we have not got 4 assignments, and therefore, we need to try and get the 4th assignment. So, we followed the procedure where we ticked some unassigned rows and drew lines. So, we ticked unassigned rows. If there is a 0 in a ticked row, then we ticked the corresponding column. We ticked the unassigned rows. If there is a 0, tick that column, and if a ticked column has an assignment, tick the corresponding row. Do this till no more ticking is possible. Draw lines through unticked rows and ticked columns. So, the lines were drawn through unticked rows. These 2 are the unticked rows. This is a ticked column, and we then drew this lines. 3 lines we drew, and we also said that these 3 lines correspond to the fact that we have made 3 assignments, and we also understood that these 3 lines are the minimum number of lines required to cover all the zeros. So, we did all that. Then what we did was, we looked at the other positions where no lines were passing, and then we found out the minimum of them, which happened to be 1, which is either this one or this one, theta is equal to 1. And then we said that we will subtract this theta, which is 1, from every element which does not have any line passing through. We will add this 1 to positions where 2 lines are passing through, and we will retain the rest of them as they are. So, that resulted in this 4 remaining as 4. This 2 has 2 lines passing, so 2 became 3, and this 2 does not have any line passing, so this 2 became 1. These 1s became 0, and we got a resultant matrix. At that point we said that we are adding something to some quantities, we are subtracting from some positions, and we do not do anything to some other positions. Another way of looking at it is, if we take a typical row, here the row is either ticked or has a line passing through. So, if the row is ticked and does not have a line passing through the entire row, then it will either have elements where only one line is passing or elements where no line is passing. So, if we take this typical row, then we would have subtracted from some positions and kept some positions the same, the 0 positions the same. If we look at this row, which for example has a line passing through, then we would either keep some positions same and add. So, that is what happens in the rows. If we take a row, we either do this or that. We either keep certain things fixed and subtract, or keep certain things fixed and add. So, that is the change that we make in the new column. Similarly, if we take a column, if we take this column where a line is actually passing through, we either keep things as they are or we add. If you take this column where line is not passing through, then we either subtract or keep things as they are. So, this process of adding the theta to the intersection elements, subtracting the theta from elements where no line is passing through, and keeping the rest of them as they are, is like redefining the u's and the v's. Now, the original u's were 4, 5, 9 and 6. Now, the new u's are 4, 6, 9 and 7. How did we get this? These are the positions where there are ticks, which means these are positions or rows where there is going to be no line, because we draw line only through unticked rows. So, it is a ticked row, so there is going to be no line. So, if there is no line passing through a row, then add theta to that u. So, 5 becomes 6, 6 becomes 7. If there is a line passing through that row, then keep the u as it is. So, u1 becomes 4, u2 becomes 6, u3 becomes 9, u3 has a line, so the u remains, u4 does not have a line, so u4 is equal to u4 plus theta, so 6 will become 7. Similarly, if you take the 4 columns, if the column does not have a line passing through, keep the v as it is. So, v1 is 0, v3 is 0, v4 is 3. If a column has a line passing through, then subtract theta from that v. So, v2 becomes minus 1. So, now we have a new set of u's and v's which correspond to the new table. Now, when we have this new set of u's and v's, the way we have defined it, we now observe that the new set of u's and v's are such that ui plus vj is less than or equal to Cij. We now realize that this set of values that we have now, if we call this as C dash ij, if we call this as C dash ij, then this C dash ij is equal to Cij minus ui plus Vj. Let me explain this. For example, if we take this element, the 2 has become 3 here. So, let us see what happens. Now, this 3 is Cij minus ui plus Vj. Ui plus Vj is 4 minus 1, 3, Cij is 6, 6 minus 3 is 3. Suppose I take this 4 where no change has happened, ui plus Vj is 4, 8 minus 4 is 4. If we look at this 1 where 2 has become 1, ui plus Vj is 6 plus 0, 6, 7 minus 6 is 1. So, the transformation from this matrix to this matrix, what actually happens is, we look at this matrix and after drawing the lines, wherever an element has 2 lines passing through, we add the theta, wherever one line passes through, we keep it as it is, no line passes through, we subtract theta. So, it looks as if we are doing something, in some places we are adding, some places we are subtracting and so on, but there is an order and there is a reason for doing this. Now, this whole thing of adding theta to the intersection element, subtracting theta from elements that have no lines and keeping the one line elements that have one line passing through them the same is equivalent to redefining the u's and v's such that ui is ui, the same ui remains if the row has a line, and ui is equal to ui plus theta if the row does not have a line. It is also equal to Vj is equal to Vj when there is no line, which means the v's are the same, and Vj is equal to Vj minus theta when there is a line passing through a column. And by redefining the u's and v's, we are now creating another Cij minus ui plus Vj matrix. And we also make sure that this matrix is greater than or equal to 0. Every element in this matrix is greater than or equal to 0, which means this matrix also satisfies ui plus Vj less than or equal to Cij. Therefore, the new set of dual variables which are got from the original set of dual variables by theta, adding or subtracting or retaining the theta, is also feasible to the dual. And it is also interesting that ui's and vj's are unrestricted in sign. So, we are not really worried about the fact that the v2 has taken a minus 1, because by definition ui and vj are unrestricted in sign. Therefore, the new matrix that we have obtained is also dual feasible, and the new matrix that we have obtained now has a corresponding u and v such that ui plus vj is less than or equal to Cij. Now, in the new matrix we would only make assignments in 0 positions. For example, we look at the first row and we say that we can make an assignment here, which means this 0 will go. We temporarily leave out the second and the third rows, we make an assignment here, this goes, and then we make an assignment here, this goes, and we can make an assignment here to get 4 assignments, and therefore we have got the optimum solution. Why? Because we make assignments in 0 positions. So, once again in a 0 position, Cij minus ui plus Vj is equal to 0. Therefore, ui plus Vj is equal to Cij. The constraint is satisfied as an equation, the corresponding dual slack is 0. So, a primal variable can be basic only when the dual slack is 0. We make assignments only in 0 positions. Therefore, we satisfy complementary slackness conditions. Therefore, the moment we get a feasible solution with 4 assignments, it is indeed optimum. But we also do something interesting between this table and the other table. Now, by looking at this theta, theta is equal to 1 here, theta is equal to 1 here, and look at this position, we actually in this position we increase the number. Even if we had a 0 and if 2 lines were passing through, we would increase it. Now, when we apply this procedure and we see if we actually had a 0 here instead of this 1, allocating into that 0 is going to take away the chance of doing this and doing this. A 0 that now has 2 lines passing through is actually an unwanted 0, and that is not going to help. Therefore, we add. But more than that, what we ensure is from here there are 2 places where we have this 1, and these 2 have become 0 in the next iteration. So, we create at least 1 new 0 in the next table. We create at least a 0 in a new position in the next table, which is a case where or which provides us with an opportunity to change the solution and perhaps get an extra allocation. So, this idea of having a dual feasible solution, ensuring that the dual solution is feasible, ensuring complementary slackness and getting an optimum solution when the primal becomes feasible generally comes in category of what are called dual algorithms. Now, here by changing the dual from one set of dual variables to another and relating them through a parameter called theta and getting a new dual solution, and also making sure that the new dual solution gives us an opportunity to have a different allocation in the primal is what is called a primal dual algorithm, and this Hungarian algorithm that we have seen is an example of a primal dual algorithm. But the basic principle remains the same. The Hungarian algorithm works on the principle that by doing this row minimum and column minimum subtraction, we are defining dual variables, and by ensuring that after the row column subtraction the matrix is greater than or equal to 0, we are ensuring feasibility to the dual. By allocating in 0 positions, we are maintaining complementary slackness, and when therefore the primal is feasible, it is optimal. Now, when the given matrix is unable to give us a feasible solution, we do this lines, we draw the lines and then we subtract theta from some positions, we add theta to some other positions and keep other positions the same, and that is equivalent to defining a new set of dual variables consistently, such that the new set of dual variables is also feasible because the new matrix is also greater than or equal to 0. But the new set of dual variables gives us an opportunity to create new assignments, and that is how the Hungarian algorithm actually works. In the next module, we will introduce how to solve linear programming problems up to transportation and assignment using some solver. So far we have solved all these problems by hand or by algorithms and we have explained the algorithms. Now, we will also explain how we can use solver to try and solve these problems. So, the next set of modules and the next set of classes will address this issue.